Chapter 5, Section 8, the kinetic molecular theory of gases. I know for sure the first time I heard about this, my feeling was, I'm just absolute blind. I didn't hear anything that the professor said. So my hope is that I've divided this up into I don't know, clean enough little pieces that it'll make some sense to you, because I do think that it is accessible to this level of class. All right, so kinetic molecular theory of gases, big words. Watch what this means. So first of all, in the kinetic molecular theory of gases, the first principle, I'm essentially reading to you off page 201. Okay, there's three assumptions or postulates that are used in the kinetic molecular theory. And the first one is that the particles have a negligible size. Okay, in other words, they're so small we can neglect their size altogether. This is the graphic that's used for it. Actually, so if you look in the margin, this is figure 5.15, and it says a model for gas behavior. The kinetic molecular theory of gases, a gas samples model is a collection of particles in a constant straight line motion. We've seen that before. So these particles are all going around, and they're mostly just going in straight lines. Occasionally they hit each other, right? And occasionally they hit a wall and bounce off, okay? First thing is, number one, they're really small. Like zero. Negligible, okay? That's how big they are. They're zero, okay? The second one is not so obvious. Do I have a graphic for this one? No, that's the last one. The second one is, okay, so number one. Let me go back to this number. Number one, they're small. Size equals 0, okay? Number two, the kinetic energy is proportional to the temperature. All right? Just look at that. Kinetic energy is 1/2 mv squared. And it's proportional to the temperature. We'll look at that, what that means in a minute. We actually have a formula for that. Okay? And I'll give that to you in just a moment. But, and then the third postulate is that all these collisions are elastic. That's a term from a physics course. Let me just say now what that means is that they don't deform as they hit each other. So this next one, this next slide is an example or a picture of that. So, if these two balls hit each other, they bounce off each other, and whatever kinetic energy they have going into it, they have going out of it, and whatever momentum they have going into it, they have coming out of it. Okay? That's an elastic collision. And in an elastic collision, two particles may come together and they smash in there, and that's what these little things are here, okay? They're smashing, they're deforming, all right, and then losing energy through the heat and so on, okay? So that's an inelastic collision. All right, so the first postulate is that they're small. The second one is that the kinetic energy is related to, let me write that again. Number one, they're small. Number two, Ke, the kinetic energy, is proportional to the temperature. And number three, the collisions are elastic. Okay? And that's the kinetic molecular theory of gases. We need that in order to come up with the laws that we've got. So the 5 laws, or the 4 laws that we've got, are Boyle's law, Charles' law, Avogadro's law, and Dalton's law, and we've dealt with those extensively. Okay, so the one big takeaway we're going to get from this is the root mean squared velocity. This is the root mean squared velocity. And the reason we don't just say velocity, we say root mean squared velocity, is because there's actually a distribution of velocities. And so it turns out some are going faster than others. And the distributions are described, I believe, described on page 204. It's real interesting, but we're going to solve a lot without really looking too deeply into that. So the root mean square velocity, though, is equal to the square root of 3, which is just a number, times R, which is another number. This is R in joules per moles Kelvin, okay? And so this is 8.314. R is equal to 8.314 joules per mole Kelvin, because we're not using liter atmospheres here, times temperature, which is the temperature of the gas, and this is the molar mass of the gas, but this is in kilograms per mole, I think. Let's figure that out together. Let's see. Let's figure that out. The root mean square velocity, so that's going to be in meters per second, right? 3 has got no units at all. R is joules per mole Kelvin, right? T is in kelvins, so the kelvins cross off. And below is, let's say it's kilograms per mole, right? Kilograms per mole. So I've got per mole on top and per mole on bottom. The moles cross off. And a joule is, what is a joule? A joule is equal to a kilograms meter squared per second squared, right? We looked this up. That's a definition of a joule. I Googled it. Okay. So, if that's true, I'm going to get rid of this joule and put kilograms meter squared per second squared in here. Kilograms cross off. And if the square root of meter squared per second squared is meters per second, aha, okay. So this script m is molar mass in kilograms per mole. So we're going to have to watch out for that. Usually we're thinking in terms of grams per mole. All right, so this is just a definition. Root mean squared velocity is equal to 3RT over m raised to the 1/2, or the square root of all that. Okay, I think we've got a sample problem here. Okay, calculate the root mean squared velocity of oxygen molecules at 25 degrees Celsius. Okay, so it's O2 gas, I'm going to write a little note here. Root mean squared velocity, root mean squared is equal to 3RT over, and this is in kilograms. So I'm going to say script m, it's 32 grams per mole, which is going to equal, it's 1,000 grams in a kilogram, so it looks like it's going to be 32 times 10 to the minus 3 kilograms per mole. Can you read my writing? 32 times 10 to the negative 3 kilograms per mole. Okay? R is 8.314 joules per mole Kelvin, and T is equal to 25 degrees Celsius, which is equal to 298 Kelvin. I'm basically done, right? Look at that. So root mean square velocity is equal to 3 times 8.314. I'm leaving the units out of here. I was so careful with units before, and also on the previous slide, right? Did you see how careful I was with units? I do not want to get a problem wrong because of lack of concern with that. But I do leave them off though, once I'm made sure I've taken care of everything. And this is 32 times 10 to the minus 3, right? So I can't do that in my head, of course, I guess. So I'm going to come over here and say 3 times 8.314 times 298 divided by 32 times 10 to the minus 3 equals, I'm not sure I got that right. I got to start over again, okay? 3 times 8.314 times 298 equals, I'm going to say divided by 32 divided by 1,000. And I get 0.23227. 0.23227. I don't know. Let me just finish that. 0.23227. It just doesn't seem right. Something is wrong here. 82 10 to the -3. No, I was supposed to this is, sorry folks, look, it just doesn't seem right. This -3, I should have divided by 0.001. I divided by 1,000. Just a moment here. Okay. 3 times 8.314 times 298 divided by 32 times 1,000 equals, 2.322, yeah. Times 10 to the 5 meters squared per second squared, right? Is equal to, take the square root of that, boom, 482. 482 meters per second. Wow, are you serious? Wow. Can you imagine getting hit by an oxygen molecule at 482 meters per second? Well, I have bad news for you. Very bad news for you. That is going to happen to you. Did you feel it? Because look, 25 degrees Celsius, the room you're sitting in is about that. Wow. 482 meters per second is the average velocity of an oxygen molecule. It's hitting your eyeball. Wow, be careful. You should wear goggles when you go outside every day. You should wear goggles when you get out of bed. All right, blank stares. I can't hear anybody laughing. All right, I'm gonna shut this video down and we'll move on to the next section.